Okay, so we're moving on to yet another topic from Principles of Chemistry 2, Intermolecular Forces and Physical Properties. We really need this, since I'm glad we're taking time in organic chemistry to review it. There's three kinds of intermolecular forces that our textbook calls your attention to, and they are here. Let me go get my marker. They are dipole interactions, hydrogen bonding, and dispersion forces, okay? Sometimes we call these London forces, sometimes we call them London dispersion forces, sometimes we call them van der Waals. My handwriting is getting worse, isn't it? Van der Waals forces, okay? And your textbook also calls them fleeting dipole-dipole forces for reasons which we'll discover. Okay, so first of all, let's talk about dipole-dipole interactions. Okay, so dipole-dipole interactions occur when two polar molecules line up with their opposite charges, right? So you see a partial minus here and a partial minus here, right? And a partial positive there. So the partial minus and partial positive is kind of like a charged interaction. It is a charged interaction. It's kind of like an ionic interaction, right? So acetone then, since it has a dipole moment, is going to exhibit dipole-dipole forces. Okay? The dipole-dipole attractions between the acetone molecules increases the acetone's boiling point and melting points. In other words, they want to stick around together. They don't want to go up into the air like a gas, right? So because they have this dipole-dipole force, they have a higher boiling point and a higher melting point than similar molecules without interaction, such as isobutylene, which we've got a picture of that here, right? So look at isobutylene and acetone. They're very similar molecules, right? They're similar in mass. They're similar in shape. They're very similar. But look at this dramatic difference in their boiling points. Look at that. Wow. This 56.3 degrees Celsius, that's hotter than room temperature, right? So if you poured some acetone on the bench, it'd sit there in a puddle for a little bit, wouldn't it? So, but if you put some isobutylene on the bench, it would immediately boil up, right? Look at the difference in those boiling points. That is strictly because of the dipole-dipole interactions. All right, so the next one, and I put this one in red because it's such a big deal, hydrogen bonds. Hydrogen bonds are a especially strong type of dipole-dipole interaction. More important than that, they're everywhere. And so everybody cares about hydrogen bonding, all right? Now, hydrogen bonding they are strong because they've got a partial positive and partial minus, okay? But they're defined as, look at this. They're defined as a lone pair on electronegative element. You see an electronegative element right there, oxygen. A lone pair on electronegative element and a hydrogen which is bonded to another electronegative element, right? And so there is the hydrogen bond. So what I have here sometimes, if we could say maybe an electronegative element might be generalized as Z. So I've got a hydrogen that's bonded to an electronegative element, and I've got a lone pair on another electronegative element someplace else, and we might say that the hydrogen bond is the electrostatic interaction between those two partial charges, right? That's going to be a partial minus because it's an electronegative element. This will be a partial plus because it's bonded to an electronegative element. And that dipole-dipole interaction is called hydrogen bonds. Okay? So here's another electronegative element, nitrogen, another one, right? There's a hydrogen that's bonded to an electronegative element, and therefore it makes a hydrogen bond. Okay? Hydrogen bond is huge, very important in nature. So only when hydrogen shares electrons with highly electronegative elements, oxygen, nitrogen, or fluorine, will it carry that partial positive charge. Now, the large partial positive, just a second here, where's my marker? The large partial positive in the hydrogen atom can attract the negatives on the other ones, which we said with a diagram in the previous slide. Okay? Okay, now even with these large, this is important to point out, even with these large partial charges, hydrogen bonds are still about 20 times weaker than covalent bonds, all right? But for intermolecular forces, a very big deal, okay? So look at this. Solvents that have hydrogen bonds are called Protic solvents. And Protic because that is an ionizable hydrogen. It's a proton, right? So they're called protic solvents. An aprotic solvent would be something that does not have hydrogens bonded to electronegative element. So I have an electronegative element right here, right? But there's no hydrogens bonded to it. So this cannot have, watch this, H bonds do not exist on diethyl ether. They do not exist on DMSO, right? This is a polar molecule, but there's no hydrogens bonded to the electronegative element. There's an electronegative element, no hydrogens bonded to it. It is therefore aprotic. Aprotic. A protic solvent then is, watch this, that's got a hydrogen bonded to electronegative element, and this is capable of hydrogen bonding. All right, now look at the effect this has on the physical properties. This is amazing. So if you have trimethylamine, look at trimethylamine. What is the boiling point of trimethylamine? 3.5 degrees Celsius. So if you put that on the bench, it would evaporate almost immediately, right? I mean, it's just where room temperature is about 21, 22 degrees Celsius. This stuff would make a gas right away, right? Trimethylamine would. It smells bad too. Ethyl methylamine, though, look at this. Just one difference. It's got exactly the same atoms in it, right? You see that? It's C3H9N, C3H9N. These all have the same molecular formula. But this one's got a hydrogen bonded to an electronegative element. And wow, look at that. That's body temperature. So ethyl methylamine, you could hold that in your hand. It would smell pretty bad, but you'd hold it in your hand, and it still wouldn't boil. It would evaporate fairly quickly, but it would not boil. Amazing, huh? But what about this? Propylamine, still C3H9N, and this has 2 hydrogens that are available for hydrogen bonding. 2 of them, and the boiling point goes up even more. But look at this. These 2 have hydrogen bonding, and this one does not. Look at these. These are both high, but way higher than 3.5. Okay? Another thing about hydrogen bonding is to show you how ubiquitous it is in nature. DNA is held in structure by hydrogen bonds. There's hydrogen bonds both holding it in a helix and also holding the double helix together. All of these rungs on the ladder, you've seen this before, those are all hydrogen bonds. Well, actually, okay, so there's some atoms in there too, but they're none of them covalent. All the atoms that are in here, there's a covalent molecule in here, or side chain, that's hydrogen bonded to the side chain of the other guy here. Okay, so it's all hydrogen bonds that hold that together. Protein's the same thing, which I don't have a picture here for you on that. Now, the last force that we're concerned about is London dispersion forces. If 2 molecules are not polar at all, they still have an attractive force between them. How? How is that possible? How can the 2 molecules be attracted to each other if there's no polarity at all? It is because of transient forces. Nonpolar molecules have their electrons spread out evenly, but there is some transient random motion within their molecular orbitals. Let's take a look. The constant random motion of the electrons in the molecule will sometimes produce an electron distribution that's actually very short-lived but not evenly balanced for a very short time. So watch this. You might, in some instant, have an extra negatives over here. Extra negatives over here. And when you do that, it's going to push the other electrons on this guy over here, right, to the red. This very transient, very short-lived disparity of electrons is going to produce something we call London dispersion forces, or van der Waals forces. So watch. Look at it. At one instant in time, they might be negatives over here, okay? And then in the very next instant, wait, I don't have that here. No. In the very next instant, the electrons might like shift over to the other side, okay? In which case, it's going to cause all the molecules around it to get pushed and pulled around too, okay? This fleeting interaction is what we call London dispersion forces. It's very weak, right? Because it's so short-lived. But like any other weak attraction, if there's enough of them, they can add up to be significant, like you might consider Velcro. The example I've got for that is the Gecko, okay? So the feet of the Gecko, you may look at the feet of the Gecko, they're not sticky. how can a gecko walk up a wall? It can walk up a wall because of London dispersion force. It's got tiny little hairs on the bottom of its feet, increasing huge amount of surface area. And what that does is that produces fleeting dispersion forces between its feet and the wall, and there's enough of them that it can cause the gecko to actually walk up the wall. Okay? London dispersion forces are the reason why molecules with more mass generally have higher boiling points. So look at butane, C4H10, right? That's got 4 carbons in it. Pentane's got 5. Hexane's got 6. And look at the boiling points. 0, 36, and 69. Okay? Now, interestingly, if we take these 3 molecules that all have the same molecular formula, C5H12, 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 all 3 have the same thing, but this one's got more surface area. Can't really tell that by looking at it because we've got it in what size font and all that, right? So we spread it out on the paper. You really can't tell which one has more surface area by looking at it, but it turns out this is more ballish, and this is more like a pencil. Okay, and so the pencil has more surface area, and look what the boiling point does. 36, 28, 10. All right, so the more branching, the less surface area, the lower the boiling point. All right, and so that's it for intermolecular forces.